Welcome back again to the PMDK Developer Day. Next up is Igor and Sergey, and they'll be presenting on the concurrency in failure atomic data structures when used on persistent memory. Igor, you have the floor.
Okay, hello everyone. My name is Igor Chorazewicz, and along with Sergey, we will talk about concurrency in failure atomic data structures on persistent memory. First, I will introduce several concepts of persistent memory programming, which are pretty important to understand the concurrency problem. So this will not be a full tutorial on how to use PMDK library, but I hope it will allow you to understand the core concepts. And after that, I will move on to the multi-threading for persistent memory, and I will talk about transactions and how they play with concurrency, and also a little bit about load-free programming. So parts of this presentation may be pretty hard to understand if you haven't got any previous experience with persistent memory, but I hope that some concepts like visibility versus persistent, which is pretty important for all applications on persistent memory, that you will understand that and will know how to deal with it. Next, Sergey will talk about concurrent data structures, and he will introduce two data structures which we expose to the users in our libraries. Those are concurrent map and concurrent hash map. And at the end, we will talk about integration of those data structures in PMDK, and we will point you to some more resources. Okay, so when talking about persistent memory, it's very crucial to define when a store is actually considered persistent. On this slide, you can see two red boxes. The bigger one, which is called PIDR, covers all the components to which a store travels to the DIM. So it means that any temporal store, for example, a move instruction, like you can see on this example, can be treated as a persistent one as soon as it enters CPU caches. To achieve that, there is usually some kind of UPS, battery or capacitor to flush the caches on failure. This approach might seem very convenient, and it actually is. However, it is also quite expensive, and very often the power fail domain consists only of the memory controller and the DIMMs. And this is the smaller red box, ADR. In the second case, in the case of ADR, any store which is in CPU caches is not actually persistent, but may be visible to other threads. And this difference between visibility and persistence is very important for understanding concurrency problems. And in general, in persistent memory programming, as was also told by Piotr, for example, in his presentation. So to ensure persistence, programmer must manually flush the data from the CPU caches in the ADR approach. This can be done by using one of those instructions which are listed on this slide. For example, CLWD and the fence instruction. It is also very important to know that only 8-byte stores are atomic on Intel processors. So the atomicity here means that either all bytes of a value will be updated on PM or none. And as I said, this guarantee only holds for 8 bytes. So to illustrate this power-free atomicity, let's look at the following example. So on the left, you see that we update a single 8-byte value. Intel architecture guarantees that you will either have the old value, so 0, or 1024, so the new value. You want to get a mix of an old and a new value. However, if you look on the right, you see that here we try to write more than 8 bytes, a string which contains a hello world. And after that, we also call persist. In this case, we have a problem because the outcome can be basically any combination of old and new value. You can't have any assumptions in this code on what the value will be in case of a power failure. So in other words, writing more than 8 bytes nor persisting this value is not an atomic operation. If there is a power failure, the outcome is undefined. In this presentation, in the examples we will show, we'll be using LOAD-PMOpch. It is a part of the PMDK library, and it is basically a transactional object storage system for persistent memory. It provides synchronous ACID-like transactions, a failure atomic memory algorithm, and some other facilities like methods which allow you to flush data, flush cache lines in an architecture-agnostic way. And LOAD-PMOpch supports both ADR and EADR. You can detect that based on a platform you are using and either flush the caches or skip them. On the bottom of the slide, you can see links to both LOAD-PMOpch and its bindings in C++, LOAD-PMOpch CDP. As I said earlier, only 8 bytes stores are atomic. So if we want to make modifications of bigger amount of data, we must use mechanisms like transactions. So in LOAD-PMOpch, transactions guarantee atomicity, consistency, durability, and optionally isolation. And those transactions are implemented using undo logs. And here is the example of how undo logs work in general. So before I will describe the picture here, I will just reiterate that atomicity here is understood as a power fail atomicity. So either all the data is there stored on persistent memory or none. And in this example, you see that we try to modify a double linked list. We try to insert a new node. So to do that in a consistent manner, we have to first record all the values of next and pref pointers in this undo log buffer. So you see that in the how row in this table, we store all the values. And only after those values are durably stored on persistent memory, we can update them with values so that they point to the new node. And if there is a crash anywhere during this procedure, we can safely restore a previous consistent state of our double linked list by looking at the values which we saved, which are also called snapshots, and we can just put those values back in the original to the original pointers. So after a crash, we will just roll back all the changes. There is also an alternative approach how we might implement atomicity for transactions, and those are redo logs. So in this approach, instead of modifying data in place, we write new values to our redo log buffer. Once this is done, we set a finish flag, indicating that this redo log is ready to be applied. And as before, you can see on this slide, addresses of next and pref pointers are stored in the what row. So those are the places which we want to modify. But in the how row, we now store new values. So the values which we intend to write. And in this approach, if a crash happens before this finish flag is set in redo logs, no recovery is needed at all because the original data has not been modified. However, if the crash happens after setting this flag, this means that some or all of the data might have been changed. In that case, we can just reply all the operations on recovery. So this means that unlike the unlock approach, on power failure, we will just redo the changes instead of recovering to the previous known state. As you can see on this slide, we can also store allocation intents in this read log. So here, the allocation intent is to allocate a new node in the list. And until the read log is completed, so until the finish flag is set, this allocation is treated like a volatile memory reservation. And as I said, there are some differences between unlocks and read logs. And from a user perspective, in read logs are can be harder to implement a generic algorithm because changes are not instantly visible. They are first stored in a regular bucket. However, it turns out that this property makes read logs a pretty nice fit for concurrent programming. And I will talk about that in a future slides. So one additional note here is that LPM-opt transactions are actually implemented as a combination of unlocks and read logs. Unlocks are actually used only to protect data modifications. So we snapshot data which we want to modify, but allocations are handled by read logs. Okay. Now let's move to multi-threading on persistent memory. This was just a general introduction. So let's first consider transactions and unlocks. So imagine we have one global variable, here A, and we want to update this variable from multiple threads. So what you can do is you can start a transaction in 2 threads, snapshot this value to make sure it is protected in case of a power failure, and increment that. As you see in this example, one thread aborts the transaction, and the second one commits. So this example is not correct. As you might imagine, modifying the data which is not protected by any logs and snapshotting it might lead to inconsistent state. Imagine that thread number 2 committed and thread number 1 aborted just after that. So because those threads do nothing about modifications made by the other thread, the value which we will restore will not take into account changes made by the second thread. So even if thread number 2 successfully completed and incremented the value, thread number 1 might just throw away those changes, which will cause data inconsistencies. So as I said, PMOps transactions support isolation, and you can use log-based approach to support this. So here you see a fixed example. You can see on PMM there are actually 2 possibilities how you can use logs. You can use either regular volatile logs managed by your application, or use PMOpt PM-aware logs. So those PMOpt PM-aware logs can be safely stored on persistent memory, and they are automatically reinitialized on each process restart. In this example, you can see that we store PMOpt mutex, which has an API very similar or even the same as the standard mutex from C++ standard library, and we can pass reference to this mutex to a transaction. The effect of that is this lock will be called for the entire duration of the transaction. So in this example, those transactions will be actually executed serially, and it will protect us from any data inconsistencies because each thread will be aware of the changes made by the other thread. Okay, but you might think that using logs to update just a single variable might be an overkill in some circumstances. So natural question is whether we could use log-free algorithms on persistent memory. So whether we can use fetch and add instructions or concurrent swap. The answer is if we are using ADR, so we need to cache flashes on failure, and this is not so easy. We cannot just use atomic operations because of the persistence and visibility problem. So because we must manually flash all the data after write, this is a separate instruction. So writing the data is one instruction and flashing is the second one. To make it work for log-free algorithms, those two would have to be a one single step. So to illustrate that more clearly, let's look at some examples. So here you can see an algorithm of inserting a tail of the list in a log-free manner and with the help of concurrent swap instruction. So on the left side, you see an initial state of some list. It contains 3 elements and the volatile domain is exactly the same as persistent domain. So it means that all the threads see all the values which are actually stored on PNet. Now let's imagine there are 2 threads. Thread number 1 tries to insert tail with number 4, with value 4, and there is also a second thread which wants to insert tail with value 5. On the right, you see a state after the first thread succeeds. So it managed to do concurrent swap instruction on current tail of the list and inserted its own tail with value 4. However, this thread might have been preempted just after using concurrent swap, but before calling flash instruction. As a result, you can see that the volatile state is different from a persistent one. And this is problematic for data consistency because if thread number 2 proceeds in this scenario, he will see that there is a new tail, he will insert his own value at the end of the list and possibly call a persist. However, if you think about the recovery procedure, the value 4 might not be linked in the list at all, right? Because this thread was preempted and crash could have happened before it continued to execute. So even though thread number 2 succeeded, the value might not be visible after restart. And this is all because visibility and persistence is not the same. So in other words, this instruction which we are using, compare and swap or compare exchange, and flashing instruction is not a single atomic instruction, but actually 2 instructions. Okay, so that was an example of compare exchange, but what about normal atomic store and load instructions? So here you see an example of some algorithm which updates 2 variables. There is a variable A stored on P1. You can assume it's 8-byte value, and there is variable B. The first thread stores writes 1 to this value A and then persists it. The second thread loads the value from A, and if it's 0, it takes some action. In this example, it modifies variable B and also persists this variable B. If you think about persistence and visibility in case of the first thread, you will see that at the time of writing the visible So after writing 1 to the variable a, the visible state will be 1, but the persistent state is really undefined. So it can be either 0, the initial value, or it can be 1, because, for example, there was some random cache addition. Only after we called PMPersist, we can be sure that the visible value and persistent are the same. But the second thread takes action, again, only on a visible value, not on a persistent one. So, on recovery, when you think about possible values of A and B, you will see that we can actually get all combinations of ones and zeros. So the A and B can be both 0, A can be 1 and B can be 0, both can be zeros, and, which is maybe quite surprising, A can be 0 and B can be 1. This last combination is not something you would expect in a normal volatile program. However, in persistent application, this is actually a valid combination in this code in case of a power failure. And this is because we once again took action on a visible state and not a persistent one. So actually, there are some ways that you can fix this code to get rid of this unwanted combination. And by the way, your application might be fine with this combination. However, when designing the data structures, we want to make sure we have a model in which we can pretty easily reason about. So, like in databases, we have a strong consistency model. It's very similar in persistent memory program. So, one way of fixing the previous example is using a PMPersist call just before we take any action in the second thread. So once we read the value of A, we persist the A explicitly and only then modify the value B. So when you think about that, this PMPersist call will make sure that the value A is actually persistent after it completes. So it's pretty clear that the unwanted combination is no longer possible in this case. So although this approach solves our problem, it is unfortunately quite expensive because if every reader has to perform PMPersist, it can invalidate cache and have performance negative performance outcome. There are some optimizations which you can use, but I will not go into detail here. If you want to know more, you can ask a question or write an email, so we can share more details on that. There is also one more way we can fix our initial code, and it is by using redo logs. So instead of modifying the values in place, we can set a redo log and write that we intend to set the value A to 1. After that, we call redo log publish, which is basically setting this finish flag I was talking about in the introduction. And you basically can think of this redo log publish call as moving the variable A in both visible and persistent state to 1. Because even if there is a crash in the middle of applying the redo log, we will recover on restart and we will set the value to 1 anyway. So the second thread does not require any changes. You can just load the value and take any action based on that. Okay? And so actually in our own data structure design, we found out that this approach works pretty well, and more about that will be said in future slides in Sergey description of data structures. So you might have noticed that when talking about compare exchange example and the list, I haven't talked about persistent memory. So this was something Andy mentioned in his presentation. So if you think about how the block-free list insert procedure could be implemented, you might come up with something like this. So you have some pointer to persistent memory, which you store on stack, for example. Then you start a transaction in which you allocate some new memory. You assign reference to this memory to a persistent pointer and commit this transaction. After that, you do compare and swap to insert new tail to the list. You know that you can do compare and swap easily in a transaction, so that's why it is outside of it. However, if a crash happens before we actually did compare and swap, but after we allocated the memory, there could be a memory. And one way of fixing that is to get rid of compare and swap instructions and all atomic instructions, basically. However, and only use transactions and log-based approach. So while this is a very simple approach, it will certainly hurt performance and scalability in most workloads. So there are some other approaches which you might take, and again, this will be described in a Sergey's part about concurrent map, especially. Okay, and I think now I will pass control to Sergey.
Okay, thank you, Igor. So let me know when I can start.
Yeah. Okay, I think you're ready to go.
Yeah, thank you. So I think after the first part, you already have an impression that designing an efficient concurrent algorithm for persistent memory is a challenging task. So I mean that it's not a problem to design a thread-safe algorithm for persistent memory. We can just use a global lock, and that's it. But this solution would not be scalable, right? And to make the efficient solution for persistent memory, it's a challenging task because designing efficient concurrent algorithm is a challenge in itself, but persistent memory just add much more complexity because you should always think about visibility versus persistency. That's why we decided to make some efforts and design some out-of-the-box data structures. And at the moment, in LibPMOps CPP, which is part of PMDK, we already have two implementations. It's a concurrent map and concurrent hash map. And I will mostly talk about internals of these data structures, but you as users can use it just out of the box. It's well tested and yeah, ready to be used. So today, concurrent hash map already fully productized, while concurrent map in experimental state. So it doesn't mean that it's might have any issues, right? It's still well tested, but we just need to confirm that our design is satisfied for the user requirements. So we need feedback from customers just to make sure that we did our work right. So, and as Piotr and Andy mentioned in their introduction talk, so the importance of testing of solutions for persistent memory is significantly higher compared to the volatile memory solutions, because in case you have any issues with your design, so all issues are persistent. So if you have a persistent memory leak, if you have a memory leak, it's a persistent memory leak. If you have a data race which causes memory corruption. It's a persistent memory corruption. So you cannot just restart your application from the scratch because the state of persistent memory survives process restart. So that's why importance of the testing is significantly higher comparing to the regular workloads. That's why in our projects we run, we do a significant testing. We have a lot of test cases, and furthermore, we use Walgreen tools intensively. For example, we already using memcheck to find memory issues. We use DRD and Walgreen tools, which is suitable for finding data races and threading issues. We use PMDK, which is useful to find persistent memory issues. So when you forget to flush something, when you forget to add something to transaction, and so on. We use PM reorder, which which try to simulate crash after each store instruction. And we also use GDB to simulate crashes at the interesting point of our application. So when we just would like to test some particular part of our code and simulate crash at some particular place, we use GDB breakpoints, and we automated this process. So now let's talk about our data structures. And first, I would like to introduce some internal data structure, which might be useful in your application. So for now, we are just using it internally, but if customers would have a demand, so we have plans to expose it as a public interface. So it's a persistent thread local storage. So actually, we inherited IDE from TBB. So TBB, it's Intel Threading Building Blocks library, which already provides concurrent data structures for volatile memory. And so we just took this idea of enumerable thread local storage, which provides the thread local variable to the calling thread. So it has a local method, which just provides a reference to some memory location specific for the calling thread. But in addition, and this is the difference with regular thread local storage, we provide iteration interface, which allows to iterate through each record of a thread local storage. So it's really useful for persistent memory because threads might store some thread-specific values in TLS, and on restart, in case of crash, we can iterate through all records and do something for restore. And one of the examples, for example, we use our TLS already in our data structures, in our concurrent data structures. One common task for each concurrent data structure is how to handle size, right? In volatile case, we can just use an atomic variable. And each thread, when it's increment or decrement size, can do atomic increment and atomic increment operation. But as Igor showed in his part, it's not possible to use atomic variables inside transactions. But in algorithms for persistent memory, usually we need to do several actions simultaneously as one big atomic action from the persistent memory perspective. And in our data structures, we are using TLS to handle the size in a concurrent environment. So in our design, each thread has its own thread local variable to handle the size of a particular data structure. And on restart, we combine these values and provide a cumulative value. So this is how we already using persistent TLS. But also, it can be used to custom redo log-based solution. So, for example, we can use persistent TLS to allocate redo actions, and in case of crash, we can iterate through them on restart. So I also will show how we are using it in our data structures. So let's start from our first data structure. It's a concurrent map. for persistent memory, and our implementation of concurrent map based on the concurrent skip list algorithm. So while by its nature, so this algorithm for volatile memory was designed as a log-free algorithm, our implementation for persistent memory employs a log-based solution described in the paper, and the reference to this paper is, you can see in the top of this slide. So concurrent skip list, so it's just a quick description of idea. So it might be considered as a multi-layered, ordered linked list data structure. And on the bottom layer, it's just a regular sorted linked list. So on the bottom layer, it contains all elements inserted to the skip list. And each higher layer acts as an express lane for the list below. It allows us to speed up the search operation. And actually, it's this algorithm provides a logarithmic average time for 3 basic operations: for the search, for insert, and for delete. So on the future slides, I will describe each operations in more details. And so the logarithmic time is achieved using the following rule. So each element appears on each layer with some probability. And the rule is the following. If some elements appears on the layer I, then it appears in the layer I plus 1 on the next layer only with some fixed probability. And in our case, this probability is 50%. So using this logic, we are able to achieve logarithmic search time. In our implementation, search is weight-free, while insert employs optimistic log-based synchronization. So we are using a fine-grained locking to achieve concurrency. So we are achieving scalability of our algorithm using this fine-grained locking system, and I will talk how it works. So first, let's look how basic search works. Since the search operation, it's a read operation, so we are not modifying the state. There is no magic for persistent memory in this place. So it just works like for volatile memory. So how search works? So we always start from the highest level, layer, and we proceed through this layer until the moment the target element is greater than the current element. So if it happens, we goes down and proceed on the next layer, and repeat it for the next layer, and so on and so on. And at some point, we will came to the lowest layer, to the bottom layer, and on this layer, we will do just a regular search. For example, let's imagine we have the following skip list presented on this picture, and we need to search element with key 9. So we proceed from the highest level, and we have a special dummy node which just use it for unification as a beginner node. And we proceed from the higher level. So on the higher level, the next pointer points to the element with key 4. Key 4 is less than 9, so it's okay. We proceed to this element. Then we try to proceed on this layer, but the pointer on the higher level points to the null. So it means that we need to drop down one layer. So we go to the next layer, and again, the next pointer on the third layer also points to null. Then we drop down again, and we can proceed to the element with key 8. 8 is less than 9. It's okay. We go to this element. Then we drop down again, and then just do a regular search, and we found the element with key 9. As you can see in our search path, we skip elements with keys 1, 2, 3, and elements with keys 5 and 7. So this is how skip list allows you to, why this list is called skip list, because it allows you to skip some elements and achieve logarithmic time. as I mentioned before, our implementation of search is wait-free. It means it provides you the guarantee of the forward progress, right? And each operation completes on some particular time. It cannot hang, right? Because it's wait-free. And to achieve it, we are using atomic instruction to read the next pointer. We atomically read the next pointer using load with acquire semantics. What it means for us, since we are using atomics, we cannot use it inside transaction. This is the main point of the search. It means we have no isolation between search and insert operation, and I will show you how we solve this issue. Now let's talk a little bit about delete operation. So our current implementation does not support delete operation, concurrent delete operation. So we support and delete operation only in a single-threaded environment. So it's user responsibility to guarantee that there is no any other concurrent insert, search, or delete. So delete can be called only in a synchronous way. So why we do this? So while initial algorithm for volatile memory it was developed and illustrated on Java, and Java has a garbage collection. But on C++, we have no garbage collector, and there is some problem. So there is a way to logically delete or extract any node from the skip list concurrently. But the question is, when we should reclaim the memory, when we should physically free this memory, because some other threads might read this memory at that moment, or it might store the pointer to this memory, or iterator, and so on. On the languages with garbage collection, there is no such problems. So garbage collector automatically counts the number of references, while in C++, there is no out-of-the-box solution. There are ways to solve this issue, but it might impact performance. So we are doing some research in that direction right now, but as I mentioned, at the moment, so our delete operation is not concurrent and not thread safe. That's it. Now let's talk about insert. It's most tricky part and interesting part in our algorithm. So how insert works? Actually, it consists of several steps. So the first step, we need to find insert position. So we just do the regular search, as I described it before, to find insert position. So let's imagine we have created a new node with key 7. We randomly generated the number of layers this node will present, and in this case the number of layers is 4. So the first step, we just need to find insert position, just doing regular search as I described it before. So we find it. But in addition, we need to remember all predecessors and successors for our new node. So for example, in our case, the predecessors on each layer, it would be dummy node, dummy head, node with key 4, and node with key 5. So yeah, as you can see, it's the predecessors on each layer. Then we need to log these nodes. So for each node, we have a mutex. So and we need to acquire these mutexes just sequentially. Once we acquire these mutexes, we need to check that next pointers, which we stored during this search procedure, has not been changed after log are acquired. Because it might be a situation when some other thread might insert to the same position and change the structure of the skip list. So it means that we need to start our insert from the beginning, from the scratch. So we need to do a find again and so on. But if we look at all previous nodes and next pointers doesn't change, then we can proceed with regular insert. We just need to link the new node to each layer. And it is safe because we acquired logs to the previous nodes. So only our thread can do insert to this position because we are holding the logs, right? So it means we have isolation, but we have isolation only between inserting threads. But as you remember, in our case, search is wait-free. And search is not waiting until insert procedure completes the insert, right? It means linking all elements and persist the changes. How we solve this issue? So actually we employ persistent TLS. Persistent TLS allow us to create some custom redo log based approach. So idea is the following. We create a persistent thread local storage, and each entry of this thread local storage is intended to store pointer to the new node. So when some thread wanted to insert new node, it allocates this node and assign pointer to this node to the persistent TLS. That's it. It means that in case of crash, this node will be reachable through this TLS. So if we, for example, if crash happens before we link it the new node to the skip list, this node is still accessible from the persistent TLS. That's it. And we actually define the following rule, that in linked list based data structures, the data consistency actually means that each node is always reachable after the crash. If crash happens at any point and we have new node allocated, it's always reachable. In our case, it's reachable through TLS or through the linked list, through the skip list data structure itself. So, and actually we can divide insert into two operations. So the first one, we are allocating new node and assign it to TLS. We are doing it transactionally because at this moment, this new node is not visible to other threads, right? Because it's not linked to the skip list. But then we can close transaction and just update next pointers on each layer without transaction. In case if crash happens at some moment during insert, we can restore from TLS. So on restart, we are checking TLS, and if it contains non-null pointers, it means that we have some non-completed insert, and we can complete it after restart. So this is why we are calling it redo log based approach. This is the main idea. The next data structure is a concurrent hash map. So so the difference between concurrent map and concurrent hash map, it's the same like difference between STD map and STD unordered map. So concurrent hash map, it's unordered map. It does not support range query operations. So our concurrent hash map is built using the same idea like TBB concurrent hash map. And idea is the following. It's just a hash table when we have an array of buckets, and each bucket contains a list of nodes. So, so usually when you need to find or insert or erase an element, you are calculating the hash value from the key and find corresponding to this hash value bucket. So you find the bucket using the hash value, and that's it. After that, once you know the bucket, you just insert or find or erase the element from this bucket. And to achieve concurrency, we employ optimistic per bucket locking. And we have each bucket, in our case, has a read-write lock. And in our case, find operation acquire read logs, while insert and delete operation acquires write log. It means that only one thread can modify the bucket at a time. So only one thread can insert or only one thread can erase element from some particular bucket. So it means that we have per bucket isolation. And it's enough for our case, so we can acquire the bucket log and then open transaction. And it means there would not be any concurrent transaction that modify data in this bucket. Right? That's it. It's pretty simple. And as usual, concurrent hash map provides constant overage time for all three basic operations: search, insert, and delete. And so this is how we achieve isolation for persistent memory. So I think that's it. Just one point I would like to disclose to you. So while our data structures can be used out of the box, but you might find that the API is too low level and you would like something which is more simple. And our answer is a PMDK. We already mentioned it in our previous presentations. So PMDK is embedded key value storage. And internally, we already built two concurrent engines. It's CS-map, which is based on our concurrent map, and C-map, which is based on our concurrent hash map. So the difference is that C-map is just a key value storage, which supports only put, get, and erase operations, but it doesn't support range query. While CS-map, it's a sorted engine, it supports range query. So the API of these two concurrent engines is already scalable, and you can just use it out of the box without worrying about thread safety, about scalability. So we are doing it for you in our PMDK engines. And which is more important, our data structures, it's a C++ data structures, but a PMDK, it's a universal solution for C++, for C, for Java, for JavaScript, for Python applications. So that's it. And just to summarize what we discussed today, so I believe that the main point of our presentation is that designing efficient concurrent algorithms for persistent memory, it's a really, really challenging task. So developers should always keep in mind visibility versus persistency. And we do some work for you. Our PMDK projects already provide concurrent thread-safe solutions. So we provide concurrent data structures for C++, and our PMDK can be used in various languages. It's thread-safe out of the box, and we already provide two concurrent engines which satisfies most use cases and customer requirements. So if you need more, please share your thoughts with us. Please look into our projects. So on GitHub, you might create an issue, ask questions, or provide feedback. So also we have a special chapter in our book. So you can read book and find the chapter about concurrency where we are describing in more details the challenges of the multi-threading for persistent memory. So that's it. We are ready for your questions.
Yeah, so thank you, Igor and Sergey, for a great presentation on such a complex topic, really. So I see some questions coming on the question and answer window. The first question is, does 8-byte atomicity also apply to non-temporal writes?
Okay, I can answer this question that yes, it applies because it's a property of the hardware. Right? So it's how data is transferred from the CPU write pending, so from the CPU to the persistent memory. So even you flash the whole cache line, so physically it's transferred only as a separate chunks, and each chunk is just 8 bytes. So this is the answer, I think. I hope it's clear.
Thank you. So the next one, in your experiments, have you seen any performance comparison between persistent data structures and the data structures in volatile memory? And how does the performance compare?
Yeah, I think we often challenge it by the question that's why your persistent data structure is slower than the volatile analogs, right? For example, sometimes people just use stale data structure and ask us why our data structure is slower. But the answer is pretty simple. So the reason of our slowdown is that we are caring about data consistency on persistent memory. We are making sure that after, so on a crash event, we can restore the the state of our data structures. While for volatile data structure, it's not the case, right? They should not worry about persistence because there is no persistence in volatile data structures.
Yeah. So one more thing. Also, the reason why persistent memory data structures can be slower is, of course, the PM latency. And if you see, there are several research papers which propose different data structures for persistent memory, and a lot of them proposes to keep inner nodes of tree, for example, in DRAM, which solves the problem with latency. But of course, it also requires rebuilding the nodes on recovery. But depending on an application, it can be a good trade-off to achieve better latency at the cost of longer startup time.
Yeah, that makes sense. The next question is, would it be possible to add a persistent tag to indicate whether a variable was already persisted, so you don't have to persist on read, next read?
Yeah, so I think this regards the slide about visibility and persistence and atomic stores. So maybe let me go back to that. Yeah, so in this example, it is possible to reserve one bit in a variable to say, to specify whether this variable was explicitly flashed by the user or not. So the algorithm could look like this. You can set a value with value 1, for example, and set this bit to false. And first reader, which reads this variable, will see the bit is false, and it will set this bit and flash the variable. After that, any future readers will see the bit is set, and there is no need for additional persisting. So this way, we can limit number of PM persists to just one on the first read. And if you want to know more about this solution, you can also read a paper proposed by Microsoft in which they developed a multi-word persistent concurrent swap, and they are actually using this optimization in their algorithm.
Thank you, Igor. So we have 3 more minutes before we take the break, but Sergey, there was a question on your previous topic on the endurance, that if you have done all your testing on different versions of databases, or have you done anything on in-memory database like applications as well?
Yeah, so for now we did testing and we did experiments only for RocksDB and LevelDB, but yeah, we can do more experiments if you have a request, so just let us know your use case. So yeah, we can estimate write amplification for any workloads because the methodology we suggest it's pretty generic, and yeah, that's it.
So I think what we're going to do right now is, again, thank you all really for staying engaged and asking questions. So what we want to do is get started with our workshop. So during the break, Andy will give out the credentials for logging into our workshop. And we can use the time during the break to get settled with you all able to log in, so we can start the workshop at noon. So Andy, I will make you the presenter, and you can take it from here.
Okay, sorry, can you hear me? Not sure if I'm muted or not because the icon went away. I think I'm...
We are,
yes, we can.
Yeah.
Thank you. Yeah, the icon did something weird to me. Anyway, thank you very much. So I'm going to share my screen here. And so during the break, you are welcome to get a jump on on getting logged into the workshop. I'll put this on a slide in a second also, but the idea here is that you go to pmhack1.pmhackathon.io and you'll get a login screen like this. And the first time you log in, you click this little request access link on the bottom here. And what you need in order to request access is a workshop ID, which is set to PMDK, so it's pretty obvious. So there's the URL, and click request access, and then there's the workshop ID, PMDK. So we're going to go ahead and take the break, but I'll leave this slide up, and please feel free to log into the workshop website. I can see people are already logging in, so that's good. And we'll start at the top of the hour.